this video, we are going to look at problem 1.12 from Griffiths Intro to Quantum Mechanics, 3rd edition. We're interested in the distribution of momenta for classical harmonic oscillator, which we also looked at in problem 1.11. And we're going to rely on some of the results and information found in that problem, so it's probably best to do that one first if you haven't already. For part A, we look at the classical probability distribution rho as a function of p, the momenta. We're going to calculate in part B the expectation values of p, p squared, and also use those things to find sigma p. And then in part 3, or part C, we are looking at the uncertainty product sigma x, sigma p. We already got sigma x from problem 1.11, so we'll just go from there. And then there's a little bit of analysis that we'll talk about at the end. So we need these two equations from problem 1.11. This is just from the setup of the problem, where rho of x dx is equal to 1 over v of x times t times dx. And then t is integral a to b, 1 over v of x dx. And so, of course, once you get this integral, just plug it in there. And so that's kind of what we're doing, how we're looking at this. In order to actually apply these equations to our harmonic oscillator problem, we need the x values in terms of the momenta. And so we're going to do that by looking at the total energy, which is just our kinetic energy plus potential energy. And so kinetic energy is 1/2 mv squared. And potential energy is 1/2 m omega squared x squared. Not super helpful though, because we don't have this in terms of p yet, our momenta. So this is p squared over 2m, same exact thing, plus, and then over here we're going to just simplify this to 1/2 k x squared, where of course omega is square root of k over m. So you square omega, you get k over m, the m's cancel. Okay, so that's good. And so this is still equal to E. And then we just, like I said, we're trying to solve for x in terms of the momenta. So let's just subtract this term to the other side. So we have E minus p squared over 2m is equal to 1/2 kx squared. Let's divide both sides by 2. Multiply both sides by 2, divide both sides by k. So 2e over k minus 2's cancel, you get p squared over mk, and that's equal to x squared. So, let's just take our square roots of both sides, and you get that x, and then subscript, I'm going to do plus minus in order to match with this. You don't actually have to do that notation. I'll leave that out for now. So we'll just say that x is equal to plus or minus the square root of 2e over k minus p squared over mk. Of course, the 2e over k, we can multiply that by m over m, or just by 1. And so you get 2me minus p squared over mk. Save myself a little bit of writing. And so those are our x values in terms of momenta p. And so looking back to what we're actually trying to do, we're trying to find the classical probability distribution rho as a function of the momenta p, so it makes sense that finding x as a function of p is going to help us do that, and we'll see why as we go through the problem a little bit more. But we're also going to need a differential element, dx, which is equal to, so this is going to be plus minus, and then we actually have to take the derivative of this, so this is minus 2p over mk is the derivative of the inside, so we got to do our chain rule. We get minus 2p from here, and then still over mk, and then there's no p's here, so that part doesn't contribute, times 1/2. This is just from the power rule. It's square root, so you bring down a half. And then the inside is unchanged, 2me minus p squared over mk, but now it's raised to the minus 1/2 power, so we can finish our power rule, and then we'll have dp. So in other words, what we're really saying is that dx equals dx dp times dp. And of course, that's obviously true. But that's all we're saying here. So now we have anywhere that we have a dx, we can substitute it in with this expression right here. Let's obviously simplify it though, because we can, so why not? And as I do that, let's just do the obvious stuff first. So 2 cancels with that. The minus is going to hit the outside, so the plus sign on top becomes a minus. The minus sign on bottom becomes a plus, so we get minus plus p. And then we're going to do bracket mk times 2me minus p squared. Close the bracket, minus 1/2 power. So what I do, we had a 1 over mk, and then we had the 1 over square root of 1 over mk. And so you can actually bring that mk into the square root, which cancels with a 1/2 power of mk in the denominator of the square root. And anyway, you see the algebra works out like that. Okay, so from here we have a much better form of our element dx. And so going back to earlier, we had rho of x dx equals 1 over v of x times t dx. So really we are writing rho as a function of x, which is a function now of p, or in other words, rho is just a function of p, and we can write it as this. So rho of x before, I'll remind us, was equal to 1 over v of x times t, which is integral a to b of 1 over v of x dx. And so now we can write rho as a function of p is equal to 1 over all of this stuff. So v of x is now just v of p, no problem there. Our integral is going to go from the momentum at A to the momentum at B. And so it told us in the problem that that was from minus square root 2me to square root 2me. And so that was just given to us in the problem statement. You can review that. And then times 1 over v of p. And then dx, dp times dp. What's dx dp? That's minus plus p. And then we had the mk and 2me minus p squared, all minus 1/2 power, and then dp. Okay, p is equal to mv. So these v of p's are equal to simply p over m. And so what we get then, let me kind of do a couple steps at once. So we can see this is going to be a p over m, and this is 1 over a p over m, so that's going to be an m over p. The m is a scalar, so that's just going to cancel. The p has to stay, though, inside the integral because we're integrating with respect to p, so that's not going to cancel just yet here, but it will cancel, in fact, with this p. Okay, so that one cancels. So these v of p's are gone. We've replaced those with p over m, and 1 over v of p is equal to m over p. The m's cancel. These p's cancel on the right within the integral itself. The last thing we're going to do, and I'm sorry I'm just doing this all in one step, it's just, it's a lot of work to rewrite each of these lines, so it's good to look at as many things as possible at once. But this mk here is under a square root, and that's just a scalar, so let's pull that out front. And so, take some time to convince yourself if you're not convinced already, but we have, writing this out, rho of p is equal to 1 over p over root mk. And then we have the same integral minus square root 2me square root 2me. And then this is dp. I usually do my dp first, or whatever I'm integrating with respect to. and then this is 2me minus p squared was all that was left, and that's raised to the minus 1/2 power. And so all our cancellations work out that that's everything that's left. The reason I want it in this form is because this is just equal to pi. I did that in Mathematica because I've solved this problem before at least 2 other times by hand, and I don't really care to do it again, especially because we're going to do this integral or a similar integral in a little bit, and I will do that one by hand. But what you see is that rho of p is equal to, okay, the square root right here flips up into the numerator, so you get square root of mk all over p times pi. And so this is the distribution of our momenta as, our distribution, probability distribution as a function of momenta. Okay, so that's fine. Couple notes here. If you choose to do the integral by hand, you're going to see that the minus plus goes away, leaving all positive values. And so essentially it's just a physical argument that you have to make, and I'm not going to go into it here because it just takes too much time. But you can make a physical argument to make that minus plus go away and leave all positive values so that you're doing this as a positive integral right here. If you do want to do the trig substitution, or if you're not allowed to use Mathematica in whatever class you're taking, just set p equal to square root 2me times sine of theta. We're going to make a trigonometric substitution. Therefore, dp is obviously equal to square root 2me times cosine theta d theta. And the reason why we actually do this is because this allows us to write the quantity 2me minus p squared, which you'll see obviously shows up right here to the minus 1/2 power. But that quantity 2me minus p squared is actually just 2me times 1 minus sine squared theta, or in other words 2me cosine squared theta. And so you do that and you'll notice that one of these, that this is actually under a square root. And so it's going to be cosine here instead of cosine squared. That's going to cancel with that cosine. That's the way that you want to do this problem. What you end up getting is an integral inverse sine of minus 1, inverse sine of 1 d theta, which is really just minus pi halves to pi halves d theta. There's nothing in the integrand, so we still have the, this factor out front, and there's nothing else in the integrand, and that's what actually gives you pi in this case. Pi halves minus negative pi halves is pi. So not doing all the steps, but that's a good look at that, probably more than I intended to do, but that's fine. For part B, let's look at the expectation value of p squared, expectation value of p, expectation value of p squared, and then we'll look at sigma p, which is just obviously square root of expectation value p squared minus expectation value of p quantity squared. So that's how we'll go at this problem here. Easy way to start this problem is expectation value of p is equal to the integral of the thing that we want the expectation value of, so that's p, times rho of x dx all over, we have to normalize it, the distribution, so integral rho of x dx, no p here. This is the same thing as the integral of p times rho of p dx dp dp. We know what dx dp is, we did that before, all over the integral of rho of p dx dp dp. So the only thing different about the numerator and the denominator is that factor of p right there. That's the thing, again, that we want the expectation value of. Well, we just found in part A that rho of p is equal to square root of mk over p times pi. So this is equal to plugging that in, plugging this into rho of p, you see that on the numerator, the p's are actually going to cancel. And then the square root of mk over pi is going to cancel from the numerator and the denominator. They're both going to have that factor in there. And so what you see is an integral of dx dp over integral 1 over p dx dp. And so this is equal to, I'm going to write this out, this is going to be a long expression, square root of 2me, that integral of minus root 2me to positive root 2me, and then we have the dx dp, so that's going to be p times, we have an mk times 2me minus p squared, raised, and the bracket, raised to the minus 1/2 power, and then you have your dp. So again, this is dx dp times dp over integral, same limit, square root 2me to square root 2me, minus to plus, and then open your bracket. Again, you have mk, 2me minus p squared, and the bracket, minus 1/2 power, dp. What you notice, the m's and the k's both cancel. Those are just constants. And then what you see is something that you have to get very, very used to in quantum, which is looking for those even or odd functions, and you see that the numerator is going to be an even function. So if you actually graph the numerator, p times that quantity, 2me minus p squared to the minus 1/2 power, what you see is, I believe it should look something like this. So here's your xy axis, and it should look something like this. And so when you integrate from even bounds, minus 2me to positive 2me square root, those just cancel. So the negative portion cancels with the positive portion. And so again, what are we saying? We're saying that this is odd on the symmetric bounds, minus root 2me to positive root 2me. And so you just get 0 in the numerator. So this is 0 over something, some number, which is equal to 0. So the expectation value of p is equal to 0. We're not going to do any more work because we have made an argument that allows us to skip any more evaluation. We're not going to be totally saved from doing that extra evaluation because we do have to do the expectation value of p squared. And so let's essentially, we're going to have this whole term over here, but with an extra factor of p in the numerator. So it's going to be p squared up there instead of just p. So before I rewrite this whole thing, let's take a look at the denominator and see if there's anything we can do to simplify it, since it's going to be the same for both expectation value of p and expectation value of p squared. It's the same denominator. And we recognize this is the same integral that we've already done. This just integrates to pi. And so we can do expectation value of p squared is 1 over pi, that's our denominator, times what I circled in red there, integral minus square root 2me to positive square root 2me, with the only change being that it's p squared now instead of p. And then we have 2me minus p squared raised to the minus 1/2 power dp. I'm going to do a quick check, make sure I got the right numbers here, that I'm not going off some wrong direction, but everything looks good. So then we just define our trigonometric substitution once again, where p is equal to root 2me times sine of theta. Why am I picking this substitution real quick? Well, because this is the substitution that you know how to pick when you've done these problems enough times. And so it's not necessarily an obvious substitution, but it is a known substitution that I'm going to use. So dp is what we said before, root 2me cosine theta d theta, and thus 2me minus p squared is equal to 2me cosine squared theta. This is our substitution. So just do it in a different color real quick so it stands out from my work here that I've been doing to solve the problem. Okay, so we have that this equals 1 over pi times the integral, and then we have to say, okay, my limit previously was minus root 2me, so plug that in. Minus root 2me divided by root 2me is minus 1. Take the inverse sign. So we get inverse sign of minus 1. And then we're going to get the inverse sign of positive 1 for the same reason. So those are my new my new limits. P squared is going to be 2me sine squared theta. 2me sine squared theta. And then we have 2me minus p squared to the minus 1/2 power. So that is going to be 2me cosine squared theta to the minus 1/2 power. And then dp is going to be root, let's just do 2me to the 1/2 power cosine theta d theta. Okay. I probably could have written this a little bit more suggestively, but we have here 2me to the minus 1/2 power, 2me to the plus 1/2 power. Cosine squared to the minus 1/2 is just 1 over cosine. So 1 over cosine is going to cancel with cosine. Okay, that's perfect. Make sure I get my factors right. So this is equal to 2me over pi. Inverse sign of minus 1 is minus pi over 2. Then we go to positive pi over 2. Sine squared theta d theta. Sine squared theta is obviously a well-known integral. And so that is just equal to 2me over pi times theta over 2, I believe. Yeah, theta over 2 minus sine of 2 theta over 4 at the limits. So minus pi halves to pi halves. You'll see that whether you plug in pi halves or minus pi halves, this term goes to 0. That's not going to contribute. And so you just get pi fourths minus negative pi fourths, so that should be pi halves. And so this is equal to 2me over pi times pi over 2. Pi's cancel, 2's cancel, and that is just equal to m times e. So in other words, we found that the expectation value of the momentum squared was just equal to mass times energy. Okay, and then the final thing that this problem asked us to do was to find sigma p. Sigma p is square root of expectation value p squared minus expectation value of p quantity squared. Expectation value of p was 0, so expectation value of p quantity squared is going to give 0. And then we just have the square root of the answer we just found, so square root of m times e. Sigma p equals square root mass times energy. Great. For part C, we have sigma x times sigma p is equal to what? That's our uncertainty relation. Sigma x we already found in the previous problem to be some normalization. I believe that's what the a was, but that's usually what a is. So a over root 2 times sigma p, which is root me. So therefore, our sigma x, sigma p is equal to a times me over 2. And I don't exactly know fully everything that this problem was trying to get at, but I think I understand the gist of it for sure, and that's that obviously when you take the limit as e goes to 0, then the uncertainty relation goes to 0 classically, right? That's classically what you expect. However, what we find is that in quantum mechanics, it doesn't go to 0, In fact, for a quantum harmonic oscillator, E is always going to be greater than or equal to h bar over 2. We can't have less than that energy. And so, obviously, with omega being, once again, that's the square root of k over m. And so the point is that sigma x sigma p is equal to a times square root m times e, but that's h bar omega over 2 at a minimum, all divided by 2. So that's square root of m h bar omega over 4. So we can take the 4 out of the square root, pull it out front. That's a over 2 times square root m h bar omega. And I think that's what the problem is getting at here. When we plug in h bar omega over 2, we can't take the energy to 0, and so we're left with some uncertainty. And so that just about wraps up the problem.